Let's look at how you evaluate how accurate a classifier is going to be. We already talked a little bit about this. If you want to measure the accuracy of a classifier, and often we do, the way to do that is to get a labeled data set and use that to measure how often the classifier is correct. So we start with a data set where we know the correct labels. And then we compare what the classifier predicts to what the true labels, the known labels are. And we can use that to see what fraction of the time the classifier's predictions are correct and what fraction they're incorrect. If our labeled data set is sampled at random from the population, then it should be representative of the population. So the performance of our classifier on that data set should be representative of the population. In other words, if it was 80% accurate on that data set, then it should be, we should expect that our classifier will be about 80% accurate on the population as well. Okay, so the picture looks something like this. We start with a labeled data set, then we split it into a training set and a test set. The training set data is going to be used to derive the classification rule. That's what the nearest neighbors classifier will use to make its predictions. And then the test set is set aside. And when we want to compare the classifier's predictions to the true labels, we do that comparison using items in the test set. So let's see what that turns into in code so that you know how to implement this. We're going to work with the same example. We already built a nearest neighbors classifier, and we've got this data set of the breast cancer biopsy tissue samples, the same stuff that Brittany Wenger used. And so now I'm dying to know how accurate is our classifier. So let's find out. Well, we have data on 683 patients. So we need to take that data, that's a labeled data set that we can think of as representative of the population of all people, all possible patients. And we're going to need to split that into a training set and a test set. And this should be a random split. So I write some code to do that. I decided to put 50% of those patients into the training set and 50% into the test set. That was a somewhat arbitrary choice. It might have been fine to put 2/3 of them in the training set and the remaining 1/3 in the test set. In any case, the way I did that was I randomly shuffled all the data into a random order, and then the first half after shuffling went into the training set and the remainder went into the test set. And then I wrote some code to evaluate the accuracy of this classifier we just wrote using the method I described to you. So I'll talk to you about what this code does. What this code does is it iterates through for each patient in the test set, takes the attributes of that patient and uses our classifier to make a prediction, to predict the diagnosis for that patient in the test set. And then it compares the prediction to the known correct answer. And if the classifier's prediction was correct, then it increments this variable num_correct. So by the time we've done this, we do this once for each patient in the test set. When we finished, this now has the number of patients in the test set where the classifier's prediction was correct. And if we divide that by the number of patients in the test set overall, we get the fraction of the test set where their classifier made the correct prediction. So the key bit happens here. And this line here, this line of code is what is invoking the classifier to make a prediction. And you'll notice that it's using the training set to help make that prediction. That's just how classifiers work. The prediction works depends on the attributes of the current example and the training set. Okay, so that's some code I wrote in advance to evaluate the accuracy of this classifier. And so then I decided to run this code, and I decided, I would try this. I would try a k nearest neighbors classifier with k equals 5, and I would try a k nearest neighbors classifier with k equals 1. What k equals 5 does is to make a prediction for a new patient, it finds the 5 most similar historical patients in the training set, looks at their diagnoses, and takes a majority of them. And with k equals 1, this classifier looks at the most similar patient in the training set and assumes that it must be the same classification. So we can see how we did. Not bad at all. With k equals 1, we already got 95 or 96% accuracy. Pretty good. And when we use k equals 5, we got 97% accuracy. Awesome. It's right 97% of the time. That's a pretty good classification rule. So you can see we're not doing quite as well as Brittany. Brittany Wenger got 99%. She had a more sophisticated technique. Go Brittany, you are awesome. But we did pretty darn well here. I'm feeling pretty good right now. So this shows you how this nearest neighbor classification, it might sound like kind of a simple rule, but one thing that people have discovered is that it's surprisingly good for a lot of machine learning tasks. It's not perfect. Sometimes you can do better, but as a first thing to try, as a simple method, it's often surprisingly good. The other thing you can notice here is how this choice of the parameter k affects the accuracy. When you look only at the most similar patient, you get 95% accuracy. If you look at the 5 most similar patients and average across them, you get something with a little higher accuracy. And maybe that makes a little bit of sense, that you look at not just the one most similar patient, but you're looking at 5 of them, and maybe that gives a little extra information that makes the prediction just a little bit less sensitive to noise. Okay, so not always true, but in this case, a larger value of k made the classifier a little more accurate. And with nearest neighbors classifiers, you may need to experiment a little to choose the value of k, or you'll often do relatively well if you just decide in advance, I'm going to use k equals 5 or k equals 10, good enough, and not try to fiddle with it. Okay. Now I want to make one last point. At this point, you know how to evaluate the accuracy of a classifier and measure how accurate it'll be. And for instance, you'd now be in a great position to talk to a doctor and say, hey, if you go adopt this nearest neighbor classifier for making diagnoses, I think you'll probably be about 97% accurate. 3% of the time you'll make a wrong diagnosis, but it's still pretty good. I want to make one more comment about why we did this splitting between the training and the test set. And that's actually really important. Folks who are new to machine learning sometimes are tempted to take that training set, learn a classification rule, and then go evaluate the accuracy using the same training set. And that turns out to be a serious mistake. So I could show you what happens if we do that. I'll show you what happens by learning a classification rule using the training set, and then our evaluation is going to go be and use those same instances in the same training set and look at how often the classification rule is correct. And do you see what happened here? What happened here is the accuracy numbers were a little different. And it's probably most noticeable if we look at the case where k equals 1. We see that when we did this bogus procedure, learn a classification rule from the training set and then apply it to the instances of the training set and see how often it's right, got a number here of 1.0, which makes it look like our classification procedure is 100% accurate. It sounds awesome, but it's a lie. We're fooling ourselves. not actually as good as it might look. And the reason is that it's biased to evaluate your classifier on the same examples you used for the training set. I'll give you an analogy to help you maybe illustrate why that's biased. Imagine that before the final exam in this class, I gave you a study guide and I said, here's all the questions that are going to be on the final exam and here's the correct answers. And then you took the final exam. What score do you think you'd get? I think you could very easily get 100% on that final exam. Because I already told you all the questions and what the answers are, so you just got to memorize them and you can get 100%. You could get 100% even without understanding anything in this class. All you'd have to do is memorize. So you see, that kind of procedure, if I tell you what the questions will be and the answers, and then I evaluate you on those same things that I used to teach you, it's not a very good measure of your understanding. It's a biased measure. And the same thing happens with machine learning. If we try to teach the classifier using things in the training set and then evaluate it on those very same examples, we get a biased view because we could get fooled. You could end up with a classifier that's no good, that all it knows how to do is just memorize and regurgitate and repeat back what it's seen in the training set, but hasn't learned any underlying patterns. It's just learned to memorize. That'd be a really stupid classifier that's not very useful, and yet that stupid classifier would get 100% if we evaluated it on the training set. It'd do lousy in practice. It'd do lousy on anything else that wasn't in the training set because all it does is memorize and it doesn't know what to do if you give it something it hasn't memorized. But if we evaluate it on the training set, it would look great. So what that means is don't evaluate on the training set. Evaluating on the training set is a bad idea. It gives you a faulty impression of how accurate your classifier is. You might end up fooling yourself into thinking you've got a great classifier when actually it's a terrible classifier. So to avoid this pitfall, instead we separate out some of the data into a test set. We split our data into the training set and the test set. And that separated out test set is used only for evaluating the classifier, never for training it. And that helps avoid this kind of faulty evaluation, avoid this bias. Okay, great. So hopefully what you've learned from this video is how to measure the accuracy of your classifier. And hopefully you've also seen an example where this simple idea of the nearest neighbors classifier can build a surprisingly good classifier for this breast cancer classification task.